Deep Learning with Neural Networks, the core of AI. Welcome to Deep Learning with Neural Networks, one of the most exciting and transformative fields within artificial intelligence, AI. In this comprehensive course, you'll gain a deep understanding of the foundational principles that make deep learning one of the most powerful tools for solving complex problems. This course will cover how neural networks operate, the different types of architectures, the training process, common challenges, and real-world applications. By the end, you'll be equipped to design and implement your own deep learning models. Course outline. 1. What is deep learning? Definition. Deep learning is a subfield of machine learning that uses artificial neural networks to model and understand complex patterns in data. Unlike traditional machine learning algorithms, deep learning models can automatically learn to extract relevant features from raw data, eliminating the need for manual feature engineering. History and evolution. Deep learning emerged from the concept of artificial neural networks, which were first introduced in the 1950s. However, it wasn't until the early 2000s that deep learning gained significant attention due to advances in computational power, specifically GPUs, the availability of large data sets like ImageNet, and new network architectures like convolutional and recurrent neural networks. Landmark achievements include breakthroughs in image recognition, speech processing, and game-playing AI, e.g. the AlphaGo. Deep learning versus machine learning. While both deep learning and machine learning fall under the broader umbrella of AI, deep learning differs in its approach. Traditional machine learning relies on structured data and manual feature engineering, while deep learning uses layered networks, deep neural networks, that learn features directly from raw data, such as images, audio, or text. 2. Understanding neural networks. Basic building blocks. Neurons. A neuron in a neural network is modeled after biological neurons in the human brain. Each neuron receives input, applies weights to those inputs, adds a bias term, and then passes the result through an activation function. Activation functions. Activation functions determine whether a neuron should be activated or not. Some common activation functions are sigmoid, maps output to the range, 0-1, often used in binary classification tasks. ReLU, rectified linear unit, a popular choice for deep networks. It outputs the input directly if it's positive. Otherwise, it outputs 0. TAN, similar to sigmoid but outputs values between 1-1, often used in RNNs. Layers of a neural network. Input layer, the first layer that receives the raw data, e.g. by pixels in an image. Hidden layers. These intermediate layers perform complex computations, transforming the input into meaningful features. Output layer, the final layer that produces the prediction, such as a class label in a classification task or a continuous value in a regression task. Forward propagation. During forward propagation, data flows through the network from the input layer to the output layer. Each layer takes the outputs from the previous layer, applies weights, biases, and activation functions, and passes the result to the next layer. Backpropagation. Backpropagation is the process of adjusting the weights and biases in the network to minimize error. After calculating the error at the output layer, the network works backward, using gradient descent to update the weights. This iterative process helps the network learn over time. 3. Popular neural network architectures, convolutional neural networks, CNNs. Definition. CNNs are specifically designed for processing grid-like data, such as images. They utilize convolutional layers to automatically detect features like edges, textures, and objects in images. Key components. Convolutional layers. These layers apply filters, kernels to the input data to extract important features. Pooling layers. Used to reduce the spatial size of the data, helping to decrease the number of parameters in computation. Fully connected layers. The final layers that take the extracted features and make the final predictions. Applications. CNNs are widely used in image classification, e.g. recognizing cats versus dogs, object detection, e.g. self-driving cars, and medical image analysis, detecting tumors and scans. Recurrent neural networks, RNNs. Definition. RNNs are designed to handle sequential data by maintaining a memory of previous inputs, making them ideal for time series, audio, and natural language processing, NLP. Variants. LSTM, long short-term memory. LSTMs are a special type of RNN that can capture long-range dependencies in data by addressing the problem of vanishing gradients. GRU, gated recurrent units, similar to LSTMs but with a simpler architecture. Applications, RNNs and their variants are used in language translation, speech recognition, and predicting stock prices. Transformer networks. Definition. Transformers are a relatively new architecture that has revolutionized NLP. They are designed to handle sequences more efficiently than RNNs by using a self-attention mechanism that allows the model to focus on different parts of the input data. BERT, GPT, and T5. These are some of the state-of-the-art models based on transformers, used for tasks like text generation, summarization, and question answering. Generative adversarial networks, GANs. Definition. GANs consist of two neural networks, a generator and a discriminator, that compete with each other. The generator creates new data, while the discriminator evaluates its authenticity. Over time, the generator becomes increasingly skilled at producing realistic data. Applications. GANs are widely used in generating realistic images, videos, and even art. They are also used in super resolution, data augmentation, and creating deepfakes. 4. The process of training a neural network, data collection, and pre-processing. The success of a deep learning model is highly dependent on the quality of the data. This includes data cleaning, removing duplicates, dealing with missing values, and handling outliers. Normalization, scaling the features so they fall within a similar range, helping the model learn more efficiently. Data augmentation. For tasks like image recognition, techniques like rotation, flipping, and cropping can be used to artificially increase the size of the training dataset. Choosing a loss function. The loss function measures how far the model's predictions are from the actual values. Common loss functions include mean squared error, MSE, used in regression tasks, cross-entropy loss, used in classification tasks, where the goal is to compare the predicted probability distribution with the actual distribution. Optimization algorithms. Gradient descent, the most commonly used algorithm for training neural networks. It works by adjusting weights in the direction of the steepest descent of the loss function. Atom optimizer, a popular variation of gradient descent that adapts the learning rate dynamically, making it suitable for a wide range of deep learning tasks. Overfitting and underfitting. Overfitting, when a model becomes too complex and performs well on the training data, but poorly on new, unseen data. Underfitting, when a model is too simple and fails to capture the underlying patterns in the data. Regularization techniques. Dropout, a technique where a random subset of neurons is dropped during each training iteration, forcing the model to become more robust. Batch normalization, normalizing the outputs of each layer in the network to stabilize and speed up training. Early stopping, a method where training is stopped once the model's performance on the validation set stops improving, preventing overfitting. 5. Advanced deep learning techniques. Transfer learning. Instead of training a neural network from scratch, transfer learning allows you to use a pre-trained model, trained on a large dataset, and fine-tune it for a specific task. This significantly reduces training time and the amount of data needed. Applications, commonly used in image recognition and NLP, where large models like BERT or ResNet can be fine-tuned for specific tasks like sentiment analysis or object detection. Reinforcement learning with neural networks. Deep reinforcement learning combines neural networks with reinforcement learning, where an agent learns by interacting with the environment and receiving feedback in the form of rewards. Applications, autonomous robots, game-playing AI like AlphaGo, and self-driving cars. Explainable AI, XAI. One of the main challenges in deep learning is that neural networks are often seen as black boxes. Explainable AI aims to make the decision-making process of deep models more transparent. Lime and Shap, techniques used to explain individual predictions of complex models, providing insight into which features are most important in making a prediction. 6. Real-world applications of deep learning. Healthcare. Deep learning is being used to analyze medical images, e.g., detecting tumors in MRIs, predict patient outcomes, and assist in drug discovery. Autonomous vehicles. Self-driving cars rely on CNNs and RNNs for tasks like object detection, lane detection, and decision-making. Natural language processing. Deep learning has revolutionized NLP with applications in machine translation, e.g., Google Translate, sentiment analysis, and chatbots, e.g., OpenAI's GPT-4. Recommendation systems. E-commerce platforms like Amazon and content platforms like Netflix use deep learning to provide personalized recommendations based on user behavior. Gaming. AI powered by deep learning is used to create sophisticated NPCs, non-player characters, and even AI that can outperform humans in complex games like StarCraft 2 and Dota 2. 7. Challenges and future directions in deep learning. Data privacy. As deep learning models require massive datasets, ensuring the privacy and security of this data is a growing concern. Computational resources. Training large deep learning models requires extensive computational power, which can be costly and time-consuming. Energy consumption. Deep learning models, particularly large-scale ones like GPT-4, consume significant amounts of energy, raising concerns about the environmental impact of AI research. Ethical concerns. The ability of deep learning models to create deepfakes, generate convincing human-like text, and predict sensitive personal information raises ethical questions about their use. Future directions. Federated learning. A technique that allows models to be trained on data distributed across multiple devices without transferring the data itself, improving privacy and security. Few-shot learning. A branch of machine learning that enables models to learn from a very small amount of data, addressing one of the main limitations of deep learning. AI at the edge. As hardware becomes more powerful, deep learning models are being deployed directly on edge devices like smartphones and IoT devices, enabling real-time inference without reliance on the cloud. Tools and resources for learning. Deep Learning TensorFlow, a comprehensive open-source framework developed by Google, offering tools for building and training deep learning models. Keras, a high-level API built on top of TensorFlow that simplifies the process of building neural networks. It's great for beginners and prototyping. PyTorch. Developed by Facebook AI, PyTorch is popular for its flexibility and dynamic computational graph, making it ideal for research and experimentation. Fast.ai, a library built on PyTorch, designed to make deep learning accessible and easy to use. It's popular for courses and tutorials. Google Colab, a cloud-based platform that allows you to write and run code in a Jupyter Notebook environment with free access to GPUs for deep learning tasks. Conclusion: deep learning with neural networks has revolutionized the world of artificial intelligence. Throughout this course, you have explored the inner workings of neural networks, how they mimic the human brain, and how they are used to solve complex problems across various industries. You've learned about the different architectures, such as CNNs, RNNs, and GANs, and delved into the training process, including the crucial role of backpropagation, activation functions, and optimization algorithms. By understanding the challenges, such as overfitting, data requirements, and ethical considerations, you are better equipped to navigate the intricacies of building robust and efficient deep learning models. Moreover, exploring advanced topics like explainable AI, transfer learning, and federated learning prepares you for the next wave of innovations in AI. As you move forward, you'll be able to apply your knowledge of deep learning to real-world applications, such as image recognition, natural language processing, autonomous systems, and healthcare. Whether you are aiming to build your own models, contribute to cutting-edge research, or leverage AI to solve business problems, deep learning will be a cornerstone of your journey. The possibilities are limitless, and you are now ready to explore, innovate, and push the boundaries of artificial intelligence.